3. Okay, let's talk about complex numbers. We're going to use this as an extension of polar coordinates. So we've talked about complex numbers in the sense of algebra. What we're going to look at right now is essentially the geometry of complex numbers, or the sort of geometry that you can put on complex numbers. Alright, so again, let's go back to that concept of the xy plane, alright, and a point in the xy plane. Alright, if I redefine slightly what my x and y axis mean, alright, if I use x to represent the real numbers and I use y to represent the imaginary numbers, then I can write an imaginary number x plus iy as a point in the plane xy. Right? So if I have this point over here, 2 plus 3i, and I have my real axis, which I'll call r, and I have my imaginary axis, which I'll call I, that means I have 2 on this, and my imaginary part is 3, so I'm going to put 3 on that, so I can represent that point right there, 2, 3. Alright, and you can do that with any imaginary number. You can give it a geometry in the xy plane. Alright. Now, doing this looks a lot like what I did in the polar coordinate video. Alright. When I take a point that is a complex number, so an r and an I, alright, x plus I, y, right? I can get to that point by looking at the x and the y, or I can get to that same point by looking at, again, the distance that that point is from the origin and the angle that it makes with the x-axis. And we have this conversion over here of r cosine theta and r sine theta, just like we used for polar coordinates. All right, so let's talk a couple of little details here because the notation's a little different. In polar coordinates, we called that distance r. In this case, we're calling it the distance that z is from 0. So when you think about the distance something is from 0 on the number line, you think absolute value. So when we're in the plane and we're talking about complex numbers, we're still going to think of it the same way. Whoop, it's a little big there. All right, the absolute value of z. Now, in this case, the absolute value of z, we can think about that again if I think about dropping my perpendicular here. All right, that ends up being the hypotenuse of the triangle whose sides are x and y. So my formula for the absolute value of z ends up being the square root of x squared plus y squared. All right, and for complex numbers, you would call that the modulus. All right, so you'll see that language when we talk about the absolute value of complex numbers. That's called the modulus of the complex number. All right, so if we have this ability to locate one of these complex numbers in the complex plane by looking at the angle and the modulus, or the angle and the radius, then I can use polar form here. All right, and the conversion that I'm going to use in my notation, is that the modulus of z is going to become r, and then x and y become r cosine theta, r sine theta. So my complex number that is x plus iy becomes r cosine theta plus I times sine theta, times r sine theta, sorry, times r sine theta. And we can simplify that, which is why I made that mistake, by factoring out the r, because there's a common factor of r. So normally you'll see this written this way. all right, r, and then cosine theta plus I sine theta. You may see, it's actually not in our textbook, but you may see occasionally this part right here written as C I S theta. Alright, so there's a shorthand for that, which is R C I S theta. Alright, and if you see that, what they mean is R cosine theta plus I sine theta. Alright. Okay, so when we have complex numbers in this form, alright, we have a simplified version of multiplication, exponentiation, and division. Alright, if I work multiplication using the algebraic form of the numbers, I have to FOIL that out. Then I have to worry about what happens when I square I, combining like terms, all of those things. When I divide, I have to rationalize the denominator of the fraction. And then again, that involves doing multiplication on the top and all of that. When I raise a complex number to an exponent, that's really kind of worst case scenario here, because if I have to take a complex number and raise it to, I don't know, the 10th or the 20th power, I don't want to do that algebraically. Right? So we have these simplified formulas that work if the complex number is in polar form. Okay? So I've got two complex numbers here. The first thing I want to do is put them into polar form. So the first thing I'm going to do is pick out, we'll start with z1. Alright, I'm going to pick out x is 1 and y is 1 for this first one here. Alright, so to put this into polar form, I use the exact same set of formulas that I do for polar coordinates. Alright, so I need my r and I need my theta. So r is the square root of x squared plus y squared, whoop, not actual y, y squared. Alright, so that's the square root of 2. And theta is tan inverse of y over x, so that's 1 over 1. So that's tan inverse of 1. Now I'm going to work in degrees for these problems because it's much easier to do the addition and subtraction and so forth with degrees. So that's a 45-degree angle. You know, if you prefer radians, by all means, go for it. Alright, so for the second one, I have x equals 1 and y equals negative 1. Alright, so keep in mind that is in the fourth quadrant, right? This was quadrant 1, this one's quadrant 4. Alright, so that's not going to affect r, right? R is still going to be the same, the square root of 1 squared plus negative 1 squared. So that is still the square root of 2. Theta is tan inverse of y over x, so negative 1 over 1. So it's the tan inverse of negative 1, which if you were working with the exact domain of tan inverse, you would say negative 45 degrees. Alright, but I want the 45-degree angle in the third quadrant, which of course I know in 315. That's what it is, 315. Here we go. Okay. Alright, so we have two complex numbers. Alright, this one, which is r cosine 45 plus I sine 45. And this one, which is square root of 2 cosine 315 plus I sine 315. Alright, so if I want, let's say z1 times z2. Alright, according to the formula, I multiply the r's. So I multiply the square root of 2 by the square root of 2, and I get 2. Cosine, I add the angles. So I take 315 plus 45, which is going to be 360. Yes, it is. 360. Plus I sine 360. Okay. Division would be similar. Alright, but you would subtract the angles. If I want to raise, let's say I want to raise the first angle to a power. So suppose I want to take z1, 1 plus I, and raise it to the 20th power. Alright, so now again, that's not something I would want to have to do algebraically, but because I have the polar form, I simply take the radius, which is the square root of 2, and I raise that to the 20th power, cosine, and then I say 20 times 45, because that's a 45-degree angle, plus I sine 20 times 45. Alright, so if I raise the square root of 2 to the 20th power, that's 2 to the 10th power. And I don't feel like working that out, so I'm just going to leave that as 2 to the 10th power. Cosine, oh, forgot a parenthesis there. Cosine 9900 plus I sine 900. Alright, so those formulas are easy to apply. Okay? Now, if you had to, all of those operations could be done on algebraic complex numbers. There's one operation that you can't do with algebraic complex numbers, and that is to take roots. Alright? So, to take the roots, you'll always have multiple of a complex number. Alright, the formula's right here, and again, I'm working in degrees, so this right here is 360 because I'm working in degrees. If I was working in radians, it would be 2 pi. Alright, so if I want to find the complex cube roots of 1 plus I, first thing I do is take 1 plus I write it in polar form, and since we've already done it, cosine 45 plus I sine 45. Alright. Since I want the cube root to the 1/3 power, alright, my r is going to be to the 1/3 power, which we'll fix that in a minute, but it's the angles that I need to work out. Alright, so I'm going to take those out. Right, theta over n plus 360k over n. Right? So my theta is 45 degrees. I'm doing a cube root, a third root. So k is going to be 0, 1, 2. Right? We end at 2 because we end at n minus 1. I need 3 roots. Since I'm starting at 0, I have 1, 2, 3 right there. Okay. Alright, so k equals 0. Alright, we do theta, 45, over n, which is 3, plus 360 times 0 over 3. Alright, 360 times 0 is 0, so that whole second term is 0. 45 over 3 is 15. Alright, so my first angle is 15 degrees. K equals 2. I'm sorry, K equals 1. Alright, again, 45 over 3. So 45 over 3, that term doesn't change. So that's still 15. plus 360 times 1 over 3, all right, which is 120. So I get 15 plus 120, which is 145, no, 135. 135. Right. And then for 2, oh, wait, where'd my, there it is. Okay. For k equals 2, again, we get 45 over 3, which is still 15, plus 360 times 2 over 3, all right, which is going to be 45, I'm sorry, which is going to be 15. 15 plus 360 times 2 over 3 is 240. So we end up with 255. All right, so we have our 3 angles for our 3 roots. I'm just going to come over here and separate this a little bit. All right, so our 3 roots are 2 to the square root of 2 to the 1/3. So that's 2 to the 1/2. Here, let me do that up here. Okay. Actually, let me do that down here. All right, so r is 2 to the 1/2. So r to the 1/3 is going to be 2 to the 1/2 to the 1/3, which is going to be 2 to the 1/6. All right, so there are all the pieces we need. All right, so our 3 roots are, first one, 2 to the 1/6 times cosine 15 plus I sine 15. Our second root, 2 to the 1/6 cosine 135 plus I sine 135. And our third root is going to be, again, 2 to the 1/6 cosine 255 plus I sine, oh, forgot the I, plus I sine 255. All right, so what we actually just did there by finding the cube roots was to take our xy plane that represents our complex axis and divide it into 3 equal spaces, right? I have 15 degrees, I have 135 degrees, and I have 255 degrees. Okay, that middle one's not right. Hang on. 135 would be this way. 255 would be this way. All right, and you've got equal spacing of your angles there. Okay. All right, so that's all we really need right now for the complex plane. So I'm going to stop and go on to the next video.